Okay, fine. Okay, we have been discussing about. Okay, first of all, yeah. Okay. So let us recapitulate what we have seen last class. We have started off discussing about mass transistors. Okay. Okay. So let us recapitulate what we have seen in the last class. Let us recap. Okay, we have started off understanding the IC technologies. IC technologies. So the ICs are classified based on different mechanisms. One is, for example, based on number of transistors. So IC technology can be an SSI, small scale integrated circuits. Okay, LSI, VLSI, sorry, MSI, VLSI, ultra large scale integration, and giant scale integration we have seen. Okay, and based on okay. Yeah, now if it is based on the type of the transistor, okay, so IC technology can be a bipolar junction transistor technology or MOS technology, etc. Okay, and IC technology can be classified into another way also, categorize that one, which is based on the material, used for a transistor. Okay, so it can be a silicon IC technology, or BiCMOS IC technology, etc. Right? Agreed? This is what that we have discussed in the last class. And another point also we have seen, the core element in the ICs are transistors. So transistors are the core element. Okay. Transistors are the core element. So what is the backbone for this transistor? Okay. It is for example, we are concentrated mostly on MOS related transistors. MOS transistors we would like to discuss about. Okay. So in this one, mass structure is very, very important one. Mass structure. So therefore, without understanding about the mass structure, we are not able to understand the operation of the MOS transistor. If you're not able to understand the MOS transistor, we don't know what happened in an IC. Okay, that's the reason why we were talking about mass structure. Okay, so now because the last class we have not given a detailed discussion about the mass structure because of the time problem. Now we'd like to discuss about, let us again recapitulate what we have seen in that one. Okay, so let us consider a piece of semiconductor here. Okay, so it may be a p-type semiconductor or it may be a n-type semiconductor, it doesn't matter. Okay, consider this is a semiconductor. So since its thickness is very, very high, we need to call it as bulk semiconductor. What we can call it as bulk semiconductor. It's a bulk semiconductor. Okay. For example, I'm considering the PMOS, P-type. For example, I'm considering about the P-type. P-type, bulk P-type semiconductor. So can you tell me what are the Can you tell me what are the carriers available within this one? Okay. The holes will be present, right? So therefore, some ions will be there. Ions are attached with holes. Yeah, thank you. So different type of holes will be present there. Are the free carriers that is available within the structure. These are available entirely in the bulk, right? So it's not possible to write all the time. So assuming that each and every ion has associated with free carrier, therefore these are the atoms. So by the way, this is the donor atom or acceptor atoms? Anyone from the class? Acceptors or donor atoms? So since it is actually the vacant positions are there for an electron, therefore it accepts an electron. Okay, therefore acceptor ions, acceptor atoms will be there in your bulk PMOS transistor. Okay, bulk P type semiconductor, right? Okay. Now what we want to do is that if you want to make a MOSFET or MOS transistor, MOSFET field effect transistor, especially we talk about the field effect transistor. Okay, we need minority carriers, as I mentioned previously. Minority carrier transportation is important. Minority carriers are required, and that too at the surface. At the surface. So these are the very important points that we need to remember in order to construct a MOSFET. Okay, so if you want to have a minority carriers, that too at the surface, that means we have to attract the whatever the minority carriers that is available within this bulk. We need to attract all those things, right? So that means we have a different. These are the dots. Okay, but I'll take red color. So these dots are all the electrons, for example. So therefore, these are all even. These are all minority carriers, right? These are all minority carriers. So our aim is that we have to bring all these minority carriers under the surface. Okay. So that means what we can see is that, for example, it is a three-dimensional view I'm writing. Okay. So three-dimensional view. So therefore, all these things are available. So at this, sorry. So only these electrons are occupying only at the surface portions of this one, right? Okay. So these portions are very important one. Okay. So only at the surface it is required. Okay. So in order to do this one, applying the potential difference between these two and cannot solve our problem. Okay. So this cannot solve our problem. Okay. Okay. Therefore, the carriers will move front and forth. It is not at all advisable one. Instead, what we can do is that just we have to place an oxide here. The capacitor structure we need to form. Okay. So therefore, we need to form a capacitor on top of it. Consider this is a capacitor, and consider a polysilicon on top of it, or a conductor on top of it. A conductor on top of it. Okay. So assume that this is a metal, this is an oxide, and this is the bottom one is a semiconductor. Okay. So therefore, this structure can fulfill our requirement. So our requirement is that minority carrier transportation and that too available in the surface. Okay, just what we have to do is that provide the potential difference between the top plate and bottom plate. Okay, if the two conducting plates are separated by an oxide, normally it is considered as a capacitor. Normally we can call it as a capacitor. But here we are using the metal, here we are using the semiconductor. This is called, in between that one we have an oxide. Therefore, this capacitor we can call it as MOS mass capacitor, right?
What was that? He was saying, evil.
Okay, I just removed the two students. Okay, so this is called mass capacitors. Agreed? Now, let us apply different potentials on, let us apply the potential difference between these two terminals. Okay, this is the one terminal, this is another terminal. Okay, so first of all, let us apply a negative potential. Okay, first let us apply a negative potential. Of course, we can start with the positive also. In a systematic manner, we want to move. So, for example, the case number 1, I'm talking about case 1. Negative potential or negative voltage. The negative potential difference that we have to apply. What does it mean, a negative potential difference? That means if you take this is a negative terminal, the negative terminal of the battery, we have to apply the positive terminal to this one. So that means that we are making the metal is a negatively charged material. Okay, that means we are providing more carriers here. Okay, so what we do is that here the electrons will be the carriers here now. So the negative charge we want to put it on top of the metal. Okay, so this is the negative charge I am putting on the top of the metal with respect to positive charge at the bottom. So what will happen? So since it is a capacitive in structure, electric field will be developed from where the potential difference will be formed there. Okay, so therefore the potential difference is formed from positive to negative, as you know that very well. Okay, so because of this positive electric field, this is called an electric field. All the majority carrier holes are attracted towards the surface. Okay, so towards the surface, the majority carriers are attracted. So all the majority carriers in the p-type holes are the majority carriers. They are accumulated under the surface of the oxide. Sorry, under the silicon, under the oxide. Okay, as I mentioned previously, this oxide is called silicon dioxide. How it will form, we will see later. Okay, so therefore, this is what we have to observe. Okay, so at the bottom, that we have to observe that at the under the oxide, you can see that some majority carriers are accumulated here. So this particular mechanism is called accumulation. It is called accumulation. Okay, so because our requirement is that minority carriers, but we are having majority carriers here. Okay, therefore what we do is that we apply a positive potential then. Okay, so let us apply a positive potential then. Let us apply a positive potential. So let us take this diagram only. Okay. Now we would like to apply a positive potential. That means we have to place a positive charge here, and with respect to the bottom one, negative. So if the top one is positive, means bottom one is negative. Then what will happen? What will happen? So that means we are applying the positive potential on top of it, right? We apply a positive potential on top of it. Okay, so because of that one, these carriers, whatever the carriers that we see, the holes will move downwards, right? It is repelled by the positive charge. It is repelled by the positive charge. Agreed? Okay, therefore the electric field is from now top to bottom, right? Here the electric field is in this direction. Here the electric field is in this direction. So therefore what will happen? So the negative charge is induced here, but this negative charge is not because of the minority carriers, because in a p-type substrate, okay, in a p-type bulk, very less amount of the minority carriers are there. It is not possible with a small amount of the positive charge on the metal cannot attract the free carriers inside of the p bulk. Okay, so therefore, because of this particular carriers are moving downwards, okay, so therefore, what will happen then? Here you can see that, of course, it is also observed that these things will go move down, because these move down, and is all will go move towards the ground side, towards the bottom side. Therefore, we have plenty of these ions, negatively charged ions will be available under the surface. Now, it cannot move actually. I'm saying that it's not movable. Ions cannot move, right? So unless otherwise you apply some very large potential. So, but just below that one, without having carriers, there will be a charge is only available under the oxide. Okay, so this charge we can call it as, depletion charge. What we can call it as depletion charge. That means the holes are depleted. Holes are depleted from that region. So that's the reason why we need to call it as depletion region. So therefore, the case number 2 is saying that case number 2 with a certain medium positive voltage, certain positive voltage if you apply, and immediately you notice that depleted carriers, depletion mode. We can call it as a depletion mode, or people will call it as an accumulation mode. Okay. So here the depleted of carriers is called depletion mode. Okay. So therefore here what we can say that up to this point, you observe that up to this point we have an oxide layer. So therefore from here to here there will be oxide now. Okay, so this oxide has got two parts. One part is from silicon dioxide, another part is from ions. Okay, so therefore this is what happened, the second one. But our purpose is also not fulfilled yet. Okay, what we have to apply is that I need to apply more positive, then I will see what will happen. I'll apply more positive, then what I'll see what will happen. So as we apply more positive, which means that I'm going to apply in this way. So more positive in the sense that large positive voltage that I should apply on top of it. Large positive voltage that I need to apply on it. Plus this is minus with respect to the bottom plate. Then now these electrons will try to come forward. So of course these electrons will move away, these holes move away from this region. Of course there is no doubt. Okay, these are all move forward, but these electrons move upwards. These electrons, these minority carriers are move upwards and gathered at this place. These are very, very important to note that. Okay, so for the sake of clarity, I'm saying that I want to remove these holes at this point, and I want to occupy this one with the minority carriers. Am I clear to all of you what I'm trying to say here? Please respond. So this is what our requirement. Am I clear to all of you? Please respond. Use the chat box and tell me that whether the concept is clear or not. This is what we are talking about, case number 3, more positive voltage. Okay, here we normally call it as inversion layer. inversion layer, or I can call it as inversion mode. Okay, we can call it as inversion mode. Okay, so please respond, students. So this is what we need to know about the mass capacitor. So I want responses from your side. Okay, so just don't be an ideal. Okay, so whatever the concept that I have discussed here, so everyone from the class should know about it. I'm not getting responses. Still, I'm not getting responses. Are you there? Am I audible? Students? Yes or no? Still more responses are required. So very simple concept. You don't worry about it. Thank you. So this is all about mass capacitor. These are the three important modes that we should know about the mass capacitor. Okay, so therefore we have fulfilled our requirement by this kind of the voltage, the given voltage. Okay. So it's very important to note here. One point is that note that the voltage, that means what do you mean by more positive voltage? The voltage at which the inversion layer will form is called a sufficient voltage. What we can call it as a sufficient voltage. So more positive voltage, nothing but that is the sufficient voltage. What do I mean by a sufficient voltage? The voltage is sufficient to make the surface under the silicon dioxide is filled with negative carriers or occupied by the minority carriers. Okay, so inversion. So whatever the positive voltage that we apply, we got inversion at the surface. Therefore, this particular region is completely inverted. That means whatever the previously it is positively charged, now it is negatively charged, a complete negatively charged surface under the silicon dioxide. Okay, and technically the sufficient voltage is also called as threshold voltage, popularly known as threshold voltage. Okay, so therefore this is what the electric field available here. This is called vertical electric field, nothing but we can call it as a vertical electric field. It's starting from top plate to the bottom plate. Agreed? Okay, now fine, so far so good. Now let us understand some more detail about it. Okay, for example, yeah, I have bring all the minority carriers under the silicon dioxide. Okay, fine. Now the question is that I want to move the carriers from one end to another end. I want to move the carriers from one end to another end, this end to this end. Okay, I'll consider this end to this end. How do we do this one? So in order to do this one, of course, if you want to move a carrier from one place to another place, for example, then we have to provide the potential difference between these two. Okay, please remember that. I have one point here, I have another point here. Okay, if you want to move a carrier, it may be electron, it may be a hole, whatever it may be. Okay, if you want to move a carrier from one end to another end, okay, so we have to apply electric field. Okay, we have to apply electric field. So one electric field that we have applied from bottom to top plate. Now another electric field that we are applying between these two. Therefore this one to this one. Okay. By applying, for example, if you want to move a carrier from this side, left side to right side, for example. Okay, then current, where the current will flow, how the current will flow. If the carrier is an electron, okay, I'm interested to move a carrier from left hand side to the right hand side. Then what is the current direction? With the current direction, it is from right to left. Okay, so if the carrier is a hole, for example, okay, then how the current will flow? Which direction the current will flow? It is the direction of the electron hole only. That means left to right only. Okay, so if the carrier is an electron, okay, so current will flow opposite direction. Opposite direction. This is the simple fundamental. If it is a hole, for example, I follows the hole direction. Opposite direction of electron. Okay, this is usual notation. Follows the hole direction. Okay, follows the direction. Agreed? Fine. Now it is not sufficient. Okay, of course, this electric field we can call it as a, don't forget about it. This electric field is called horizontal electric field. So it is called EH. Let me call it as, it is called EH. Okay, it is called EH. Therefore, the carrier transportation in this particular device is completely based on electric fields. Okay, therefore, that is the reason why whatever the transistor that we are going to develop or design, that is called field effect transistor. Okay, so therefore the construction is pending actually. Let us construct the transistor now. Okay, now let us construct the transistor. Of course, it is not sufficient the carriers that are available under the silicon dioxide. Okay, so it is the best practice is that we have to provide an additional carriers adjacent to that one. Okay, and we have to use additional carriers adjacent to that one. Therefore, the carriers, the plenty of carriers are available from left hand side to the right hand side. Therefore, we have a plenty of electrons is here and plenty of electrons is here. Usually, we need to call it as heavily doped carriers. So, therefore, since it is an electrons, we have to take n plus electrons only. So the heavily doped electrons only we need to consider here. Okay, therefore, whatever the left hand side, whatever the right hand side has got plenty of carriers are available. Okay, now it is right time to apply the potential difference between these two also. It is the right time to apply the potential difference between these two. Agreed? So therefore, here we have to apply some potential difference. Okay. And here also we need to apply the potential difference here. Okay, so therefore it is responsible to create a vertical electric field. It is responsible to create horizontal electric field, right? Agreed? Okay, so therefore this is called actually the field effect transistor. So because of this electric fields, it is called field effect transistor. We follow the structure called Mos structure. Therefore, it is called Mos field effect transistor or simply Mos transistor. Okay, so but it is not possible to leave the source and drain something like this, but it should be there in the bulk, right? So therefore, we have to extend the bulk from this place to this place and from here to here. Okay, so therefore this is all about the structure of the Mos transistor. Okay, so how many terminals that we can see here now? Any guess? As you can see here, one is this terminal, second terminal, and third terminal, and we have fourth terminal. Okay, therefore MOSFET is a 4-terminal device. MOSFET is a 4-terminal device. Okay, now so whatever the materials or whatever the carriers that are available at the left side, normally we can call it as source. This is called source. At the right side, whatever we have called, that is called drain. So it takes the electrons from the source. The source is able to provide the electrons. Okay, under the silicon for this under that particular area. And this is called bulk. This is called as bulk terminal. And whatever it is there on top of the metal, whatever the metal is there, that metal plate, if you take the lead outside, then it is called a gate. Then it is called a gate. Okay, so these are the terminals that we have for the particular transistor, for a particular transistor. So if you want to analyze the electrical characteristics, or if you want to understand its the different electrical properties, and all the time we are not able to draw this kind of diagram structure for the material. Okay, so instead we have a symbolic representation. That representation is shown here. So this is a small line and a large line, and take here one terminal. So I think it's better to write in proper manner. So this is the one. Okay, so this is called a gate. This is called source, for example. This is called a drain, right? So it's drain. So source and drain are the same material, same sizes. Okay, there is no difference between the source and drain, unless otherwise what potential that we are applying. Okay, so can anybody tell me in the class, if I want to move a carrier from left hand side to the right hand side, what potential that I should apply at the left hand side? What terminal of the battery I should apply here, so that the carrier can move from source side to the drain side? Anyone from the class? I want to move an electron from left hand side to the right hand side. If that is the case, what is the potential I should apply at the source, and what is the potential that I should apply at the drain? Anyone from the class? Let me check answer. Somebody has sent. Source is positive and drain is negative. Any other answers? So the question is very simple. So I want to move an electron from left hand side to right hand side. Etla move cheyalanuntunna. Aithe ikkade potential undali, ikkade potential undali. Very simple, fundamental. Yeah, you have corrected. This is what we have to do. We have to apply a negative charge, negative plate at this side, negative terminal of the battery we have to apply, so that this negative charge can repel this electron, so that it can move towards the right side. Okay, essentially the left hand side should be a negative terminal. So one terminal is a negative, another terminal is obviously a positive one, right? So this is how we need to apply. So therefore here we have to apply negative, here we need to take positive. Agreed? And obviously, if you want to apply the transistor in this direction, we have to apply the negative or positive at the plate, and of course it will be the negative, because we want to apply the positive charges intentionally on the top of the metal. Okay, and because of that one, electrons are attracted towards the oxide side. Okay, therefore first positive and negative at the top plate for the electric field. Okay, agreed? So how the terminals of the terminal charges of the transistor? Okay, okay. So therefore what we need to know that, for example, as we can observe very clearly, so what is the relationship between, because if these two are same type of material we are using, source and drain are the same type of material, same width, same length, and everything is equal normally. Okay, then how do we distinguish it is a source or it is a drain? So can't we take this is the source, this source తీసుకుని drain తీసుకోవచ్చా, ఇది source తీసుకుని ఇది కూడా drain తీసుకోవచ్చు. then how do we make the difference between these two approaches? One time we are taking that left side, or otherwise if I've changed to other side is a source, then what makes you understand that how can we distinguish between these two? That's an important one. Okay, so very simple. So if it is the carriers are negatively charged carriers. Okay, so every time we have to apply a negative charge to one plate. So that means all the time, whether it is in the left side, source is at left side, source is at right side, whatever it may be, it doesn't matter. If any material, for example, any heavily doped material, whatever the heavily doped material, if I'm applying the negative potential here, for example, then you treat this as a source, and obviously other will be a drain. Or for example, if one material is here, I'm applying the negative terminal here at this point. Okay, negative terminal of the battery I'm applying at this side, right hand side. Then immediately you assume, you have to think about it. It is a source now. It's not a drain. Okay, the point is that the electron has to move from lower potential to the higher potential. That's what the main intention for that electron. Okay, that means that the source side must be a negative terminal. Okay, so therefore, what is the comparison between these two? So source must be a negative, drain must be a positive side. Or some other way we can say that drain is at higher potential, and source is at lower potential side. So this is how also we can distinguish the source and drain of a MOS transistor. So immediately, for example, if you go to the lab, you will find that they will give you the MOSFET transistor. Then how do you apply the potential? If they say that it is an NMOS transistor, for example. If it is NMOS transistor, then what we have to do? So just to keep in mind that whenever we are applying the negative potential, that we have to treat it as a source, because it is not possible to say that it is a source, the second one is a drain. It's not like that. Okay, so by applying the potential, we came to know that one is the source, one is the drain. I hope the point is clear, right? Fine. Now, this is how we can say that the MOS transistor and its structure. Okay. So another point, let us consider. Another point is that so sometimes we can call it as enhancement type mode, or depletion mode type of transistor. Depletion mode transistor. What does it mean? This is the terminology that normally we use. Okay. So whenever we fabricate, so the fabrication steps we will see later point of time. Whenever we fabricate a transistor, something like this, source and drain, something like this, if you are not finding any kind of inversion layer, another name for this inversion layer is, I will write here itself, inversion layer is called as a channel. So this is also popular name we need to use for transistors, channel, right? Okay, the inversion layer. Okay, inversion layer, we normally call it as channel. So inversion mode means when we are applying the positive potential on the top and negative potential at the bottom, then this mechanism is called inversion mode. And particularly this region is called at the bottom. So this region is called inversion layer. This inversion layer is also called as a channel. Okay, and specifically we talk about it is a N channel. Why? Because electrons are the carriers in that particular channel. Okay, so therefore electrons are the carriers. Therefore, if I say that N channel enhancement, for example, if I usually I can say that the N channel enhancement. So N channel enhancement MOSFET. If I say like this, what does it mean? It is a field effect transistor. There is no doubt. Okay, field effect transistors are also available in other form. Also, it is called junction field effect transistors also there, and different type of field effect transistors are there. We focus on mass related structure field effect transistors, right? So this mass structured based field effect transistor has got negatively charged carriers, or I can say that the electrons under the silicon dioxide, then it is called N-channel MOSFET. And another terminology I'm using that enhancement. So unless otherwise, if you're not applying a sufficient voltage, the channel cannot be formed. Unless otherwise, if you are not able to provide a sufficient voltage, the channel cannot see here. Okay. So if you say that here, if you want to form a channel here, for example, under the oxide, is it possible without applying any potential difference between these two? No, obviously it's not possible. It's the channel cannot be formed. This channel cannot be formed. Okay, we have to apply a potential voltage here, which is the voltage that we apply here is which is greater than that or equal to threshold voltage of a transistor. That means the sufficient voltage of a transistor. Then only the channel will be formed. Such type of N-channel MOSFETs are called dip enhancement type MOSFETs. Sometimes this is called enhancement type transistors. Okay, generally in the 99%, 99.99%, we use enhancement MOSFETs only. Therefore, that's the reason why we don't want to call all the time it is an enhancement type mode type of transistor. We don't say like that. Instead, we should say that N-channel MOSFET. N-channel MOSFET, right? It is an N-channel MOSFET. Or simply people will call it as N-MOSFET. Nmos. Simply we can call it as Nmos. So either name is possible to call it as a the reason is that it is an enhanced N-channel enhancement MOSFET transistor. Okay, so but almost all the time I will use this transistor as an Nmos transistor. Okay, I call it as an Nmos transistor. You have to remember that if I say that Nmos transistor means it is an N-channel MOSFET transistor. Okay, that to an enhancement type mode transistor. We have another type of transistor that is called depletion mode type of transistor. What we can do is that, so while we are fabricating, interestingly, we have to create the channel itself. So we have to create the within the fabrication. Okay, it is not because of this channel is not because of externally applying the potential difference between the metal and semiconductor. It's not because of that. It is inherently available during the fabrication, during while we are making the transistor. So this type of transistors are called depletion mode type of transistors. Of course, it is an N-channel only we need to place. Therefore, it is called N-channel depletion mode type of transistor. Okay, N-channel depletion mode MOSFET. Okay, so so the symbolic representation of the enhancement type transistor is something like this. Okay, we write it, but it is also an N-channel MOSFET. But how do we cannot write all the time this symbol, right? We need to have a symbol for this one also. For that one, we need to consider very thick line of this terminal. This line we have to use thick line. This one we have to use. Now, this is the difference between the symbolic representation or differentiation between the enhancement and depletion. Okay, so this is the depletion mode type of transistor. This is called enhancement mode type of transistor. Okay, so that's what we need to understand about it. Okay, but what is the difference between these two? Again, so let me complete it in 1 minute, within 1 minute. Here, what we have to apply, we have to apply the potential difference between the between this one and this one to create a channel. But here we have to apply the potential difference between the metal and semiconductor to seize the or to make the channel list disappear. Okay, that means by keep on applying the potential, we can remove the channel there in that one. So in the opposite direction, opposite way that we are going to use compared to the enhancement type of transistor. Okay, so therefore by applying so if you want to remove this channel, what I have to do? By the way, if it is an N channel, I have to apply more negative here. So if I'm applying the negative here, what will happen? The channel will be decreases from that point to this much. It will be decreases, and further we can decrease something like this. Therefore, like this, we have to decrease the entire channel by applying the more negative voltage. Okay, so by applying the more negative voltage, we are going to use in our circuits to make certain kind of transistors, certain kind of circuits. Okay, so but we don't want to focus mainly on the depletion mode type of transistors. Exclusively, we talk about enhancement type mode type of transistor because these are popular and in all aspects. Why it is important, or why how the better performance can be done with respect to the depletion type mode type of transistor. All these things we'll see in the coming classes. Okay, so this is how the today's class. If we have any doubt, please send me through a WhatsApp or some other medium, or maybe Moodles. Get the things done in a proper manner. Okay, thank you. Thanks for everything. I stop here today and I will take that miss later.